In September 1942, as Allied convoys sailed through the dark waters of the North Atlantic, believing they were protected by their vigilant escorts, a silent mathematical revolution was unfolding in the ocean depths. U-96, commanded by Captain Lieutenant Heinrich Lehmann Willenbrock, had just fired 4 torpedoes at a British convoy, but this time, something was completely different. There was no characteristic bubble trail that usually revealed the submarine's position, nor the roar of steam engines that warned enemy escorts. The electric G7e torpedoes glided silently through the water like deadly ghosts, carrying 280 kilograms of explosive towards their unsuspecting targets. Dusk offered perfect cover, but it was the revolutionary mathematics behind these silent electric shots that would truly change the rules of the game in the Battle of the Atlantic. This was not just another submarine patrol mission. It was the demonstration of a weapon that would force the Allies to completely rethink their escort tactics and anti-submarine defense. The deadly equation behind these ghost torpedoes was about to redefine naval warfare, turning every dusk into a moment of calculated terror for Allied merchant fleets. The development of the G7e Torpedo began in 1936, when the German Kriegsmarine recognized a critical mathematical flaw in its conventional submarine weapons. Traditional G7e torpedoes, powered by compressed air and fuel, left a distinctive bubble trail that extended for hundreds of meters on the water's surface. This trail not only revealed the torpedo's trajectory, allowing evasive maneuvers, but it also created a mathematical vector that pointed directly to the position of the submarine that had fired it. For Allied escorts equipped with ASDIC sonar and depth charges, this trail was like a solved equation leading directly to the U-boat. Engineers at the Torpedo-Versuchsanstalt in Eckernförde faced a seemingly impossible challenge: how to create a torpedo that was simultaneously lethal and mathematically invisible. The answer came through a revolutionary approach: pure electric propulsion. Using lead-acid batteries to power a 100-horsepower electric motor, the G7e would completely eliminate combustion and, consequently, the gases that created the revealing trail. But this seemingly elegant solution would hide mathematical and engineering complexities that would take years to master through precise calculations. The mathematics behind the G7e revealed German genius in naval engineering and submarine ballistics. With an exact length of 23.5 feet and a weight of 3,545 pounds, the torpedo needed to balance power, range, and speed within the rigid limitations imposed by the available batteries. The G7e TII model could reach speeds of 30 knots, with an effective range of 16,400 feet. However, firing calculations required extraordinary mathematical precision that separated competent commanders from true submarine aces. U-boat commanders needed to calculate the gyro angle, the initial direction the torpedo would follow before activating its magnetic guidance system. This complex equation considered the target's speed, its angular direction, the distance to the predicted impact point, and the torpedo's own constant speed. An error of just 2 degrees in the initial calculation could result in a devastating error of more than 570 feet at the impact point at a distance of 16,400 feet. To further complicate this deadly mathematics, commanders needed to consider variable ocean currents, which could deflect the torpedo by up to 160 feet during a long run. Impact time was also crucial in the equation. At 30 knots, a torpedo would take approximately 5 minutes and 24 seconds to travel the maximum distance, more than enough time for an alert ship to significantly alter its course and speed. Heinrich Lehmann Willenbrock, a 28-year-old veteran with over 200,000 tons of ships sunk in his deadly record, had become a true master of this submarine mathematics. In his cramped U-96 cabin, surrounded by navigation instruments and ballistic tables, he developed calculations that seemed more suited to a physics laboratory than to a war submarine. His personal notes revealed an almost scientific obsession with precision. Target at 4,200 meters, estimated speed 12 knots, course 045 degrees, northeast wind 15 knots, current 0.8 knots southeast. Each variable was meticulously recorded and incorporated into his firing equations. Lehmann Willenbrock had discovered that the secret lay not only in pure mathematics, but in the ability to calculate quickly, under extreme pressure, when enemy escorts approached and submergence time was limited. He developed his own mental calculation system that reduced computation time from 3 minutes to less than 45 seconds. His officers watched in admiration as he mentally manipulated complex numbers, adjusting angles and speeds with the precision of a human calculating machine. This mathematical mastery was not just impressive, it was literally the difference between life and death in the hostile waters of the North Atlantic. The first time U-96 used G7e torpedoes in real combat was during a patrol mission in British waters in August 1942. Lehman Willenbrock had identified a convoy escorted by 2 Town-class destroyers and a Flower-class corvette sailing in a standard defensive formation. What made this attack particularly challenging was the mathematics involved in hitting the escorts themselves. Smaller, faster, and infinitely more dangerous ships than the slow freighters that usually constituted submarine targets. The escorts maintained a constant speed of 18 knots in a zigzag pattern, altering course every 4 minutes at angles of 30 degrees. This evasive maneuver created a complex mathematical problem: how to calculate an interception point for a target that changed direction predictably, yet frequently. Lehman Willenbrock needed not only to predict where the escort would be when the torpedo arrived, but also to consider its direction at the moment of impact. His calculations showed that a torpedo fired during a course change would have a 73% chance of error, but a shot timed for the middle of a straight segment increased the probability of a hit to 89%. The mathematics was clear, but execution required perfect timing and nerves of steel. The moment of firing arrived at 7:47 p.m., as dusk painted the ocean in shades of gray and orange. Lehman Willenbrock had positioned U-96 at a distance of 3,800 meters from HMS Veteran, a V-class destroyer serving as the convoy's main escort. Through the periscope, he watched the enemy ship cutting through the waves with its sharp bow, completely unaware of the submarine's presence. The final calculations were checked one last time. Target speed 18 knots, course 075 degrees, distance 3,800 meters, gyro angle 15 degrees to port. The G7e torpedo was set for a depth of 12 feet, ensuring impact on the hull below the waterline. "Tube 1, fire!" The order echoed in the torpedo compartment, and the first electric G7e slid silently out of tube number 1. There was no characteristic roar of compressed air, nor any perceptible vibration in the submarine's hull. The torpedo simply disappeared into the growing darkness, carrying its deadly payload towards the unsuspecting target. In the following minutes, the U-96 crew waited in absolute silence, mentally counting the seconds until the calculated impact. The mathematics had been done. Now all that remained was to await the explosive confirmation of its precision. What happened in the next 6 minutes and 14 seconds would forever revolutionize submarine warfare in the Atlantic. The G7e torpedo glided through the water without leaving any visible trace, its electric propulsion operating in total silence. On HMS Veteran, lookouts maintained their normal observation routine, scanning the horizon for periscopes or torpedo wakes, but there was nothing to see. The destroyer's ASDIC sonar system, designed to detect submerged submarines, could not identify the approaching electric torpedo. The absence of cavitation and engine noise made the G7e practically invisible to Allied detection equipment. Meanwhile, on U-96, Lehman Willenbrock mentally timed the torpedo's approach, his calculations indicating impact in 4 minutes and 30 seconds. The German crew remained in absolute silence, each man aware that they were witnessing something historic. For the first time in the war, a truly invisible torpedo was being tested in real combat. If the mathematics were correct, if the calculations were precise, if the technology worked as designed, they were about to witness a revolution in naval warfare. The fate of HMS Veteran, and potentially the entire Battle of the Atlantic, now depended on the precision of equations calculated in a cramped submarine cabin. At 7:53 and 14 seconds p.m., exactly 6 minutes and 14 seconds after firing, a massive explosion illuminated the Atlantic twilight. The G7e torpedo had hit HMS Veteran precisely at the calculated point, 18 feet below the waterline in the engine room section. The explosion of 617 pounds of G7e 36 tore a 25-foot hole in the destroyer's hull, causing immediate flooding and loss of power. But what truly shocked the British crew was not just the impact. It was the complete absence of any prior warning. There was no torpedo wake to track, no engine noise to detect, no indication that an attack was underway. For the sailors of HMS Veteran, the torpedo had simply materialized out of nowhere, as if fired by a ghost. On U-96, the German crew erupted in silent celebration. Lehmann Willenbrock had proven that his mathematics was correct. The electric torpedo was not just a weapon, it was a revolution. As he watched the British destroyer list heavily to port, he was already calculating the next shot. The corvette HMS Primrose was sailing at 2,100 meters, speed 16 knots, course 120 degrees. The numbers danced in his mind as he prepared the second G7e Torpedo. The deadly mathematics had only just begun. The reaction of the convoy's other escorts immediately revealed the devastating psychological impact of the invisible torpedoes. HMS Primrose and HMS Wanderer initiated desperate evasive maneuvers. But without a torpedo wake to track, their actions were essentially random. British commanders faced an unprecedented tactical dilemma: how to defend against a weapon that could not be seen or detected. Radio communications intercepted by the Germans revealed growing panic. Torpedo impact on Veteran. No wake observed. Repeat, no wake observed. The absence of the characteristic wake was not just a tactical advantage. It was a psychological weapon that undermined the escorts' confidence in their own defensive capabilities. Meanwhile, Lehmann Willenbrock continued his calculations with mechanical precision. The second torpedo was fired at 7:58 p.m., aimed at HMS Primrose, which was attempting a high-speed evasive maneuver. The mathematics for targets in evasive maneuvers was even more complex, requiring calculations of acceleration and prediction of course changes. The G7e Torpedo silently cut through the water, its trajectory adjusted to intercept the corvette at its maximum vulnerability point. For the Allied escorts, every minute that passed without detecting the origin of the attacks increased the terror. They were being hunted by a mathematically invisible predator. The second impact came at 8:04:33 p.m., as HMS Primrose was in the middle of an emergency evasive turn to port. The G7e Torpedo hit the corvette in the stern section, destroying the rudder compartment and causing a total loss of directional control. The mathematical precision of the attack was astonishing. Lehmann Willenbrock had calculated not only where the ship would be, but also its exact orientation during the evasive maneuver. The corvette began to spin in uncontrolled circles, its crew desperately fighting to restore control. But what most impressed the German observers was the reaction of HMS Wanderer, the third escort. Without any visual or audible indication of the attack's origin, the destroyer began firing depth charges randomly, hoping to hit the attacking submarine by sheer luck. The underwater explosions created 200-foot-high columns of water, but all missed U-96 by considerable margins. Lehmann Willenbrock observed through the periscope with scientific satisfaction. The mathematics had not only made his torpedoes invisible, but also rendered enemy countermeasures completely ineffective. HMS Wanderer was firing blindly, wasting precious ammunition against an enemy that remained mathematically undetectable. The silent revolution was proving devastatingly effective. As chaos spread among the Allied escorts, Lehmann Willenbrock made a decision that would demonstrate the true tactical genius of the G7e torpedoes. Instead of attacking the convoy's defenseless merchant ships, he directed his third torpedo against HMS Wanderer itself. This choice revealed a deep understanding of the psychological mathematics of naval warfare. Eliminating escorts not only removed convoy protection, but also sent a terrifying message to other Allied fleets. The calculation for this third shot was particularly complex, as HMS Wanderer was now in high-speed evasive motion, alternating between 22 and 25 knots while changing course erratically. Lehmann Willenbrock needed not only to calculate the target's future position, but also to predict the pattern of its evasive maneuvers. His years of experience in submarine combat had taught him that even random maneuvers followed predictable psychological patterns. Commanders under pressure tended to alternate between sharp turns and straight segments, creating a rhythm that could be mathematically anticipated. The third G7e torpedo was fired at 8:11 p.m., configured for a complex interception that considered not only the physics of movement, but also human psychology under extreme stress. HMS Wanderer was hit at 8:17 and 45 seconds p.m., exactly where Lehmann Willenbrock had predicted it would be during its next evasive turn. The electric torpedo penetrated the hull in the central section, causing an explosion that broke the destroyer in half. In less than 30 minutes, 3 Allied escorts had been eliminated by torpedoes that seemed to have been fired by ghosts. The mathematics behind this feat was extraordinary. 3 moving targets, 3 complex calculations, 3 precise impacts, all without leaving any detectable trace. But the true impact of this demonstration went far beyond the sunken ships. Intercepted radio communications revealed that news of the ghost torpedoes was spreading rapidly through the Allied fleet. Escort commanders reported sightings of torpedoes without a wake, creating a paranoia that would affect Allied naval operations for months. The British Admiralty was forced to completely revise its anti-submarine tactics, developing new protocols to deal with a threat that defied all traditional detection methods. The silent mathematics of U-96 had created a crisis of confidence that would spread throughout the Royal Navy. Every shadow in the water, every suspicious movement, every unexplained noise now carried the possibility of an invisible torpedo approaching. In the days following the attack, German naval intelligence intercepted communications that revealed the true psychological impact of the G7e torpedoes. Reports from escort commanders described an atmosphere of constant tension, where lookouts reported ghost torpedoes that disappeared when investigated more closely. The absence of visible wakes had created a situation where any disturbance in the water could be interpreted as an imminent threat. Allied escorts began wasting depth charges, attacking schools of fish, floating debris, and even their own shadows projected onto the water. The British Admiralty was forced to issue special directives instructing commanders to maintain fire discipline and visually confirm torpedo wakes before initiating depth charge attacks. But these instructions created an impossible dilemma: how to visually confirm something that, by design, was invisible. Lehmann Willenbrock and his crew observed these interceptions with growing satisfaction. They had discovered that the mathematics of electric torpedoes was not just about ballistics and navigation. It was about psychological warfare on an industrial scale. Each G7e torpedo fired multiplied its impact through fear and uncertainty, creating a ripple effect that affected naval operations far beyond the physical range of the weapons. The silent revolution was spreading through the collective mind of the Royal Navy. The Allied technological response to the G7e torpedoes revealed the depth of the challenge that Lehmann Willenbrock and his colleagues had created. British and American engineers worked feverishly to develop new detection systems capable of identifying electric torpedoes. The fundamental problem was that all existing systems relied on detecting noise, cavitation, or visual wakes, precisely the characteristics that the G7e had eliminated. Attempts to use passive sonar to detect the torpedo's electric motors proved ineffective, as the noise was masked by the ocean's ambient sound and the ship's own engines. Magnetic detection systems were experimented with, but the torpedo's magnetic signature was too weak for reliable detection at useful distances. Meanwhile, German production of G7e torpedoes was being accelerated. Factories in Friedrichsort and Eckernförde worked 24 hours a day to meet the growing demand from U-boat commanders who had witnessed the devastating effectiveness of the silent weapons. Each torpedo cost approximately 24,000 Reichsmarks to produce, a significant investment, but one that paid for itself through the ability to eliminate Allied ships worth millions. The economic mathematics of submarine warfare had been fundamentally altered by electric torpedoes. In October 1942, U-96 returned to its base in Saint-Nazaire, carrying data that would revolutionize German submarine doctrine. Lehmann Willenbrock had meticulously documented every aspect of his G7e torpedo attacks: firing angles, distances, target speeds, sea conditions, and most importantly, hit rates. His record showed a 34% improvement in accuracy compared to conventional G7A torpedoes, but the true value lay in the ability to conduct multiple attacks without detection. During its 47-day patrol, U-96 had sunk 12 Allied ships using exclusively electric torpedoes without a single effective countermeasure from enemy escorts. This data was immediately shared with other U-boat commanders through the Kriegsmarine's communication network. Karl Dönitz, commander of the German submarine force, immediately recognized the strategic implications. In a secret meeting at the Führer's headquarters, he presented analyses showing that the widespread adoption of G7e torpedoes could increase the effectiveness of the submarine campaign by 40 to 50%. The mathematics was convincing. Invisible torpedoes meant more ships sunk, fewer U-boats lost, and unsustainable pressure on Allied supply lines. The silent revolution was transforming into a decisive strategic advantage. The dissemination of G7e technology throughout the U-boat fleet created a multiplier effect that the Allies had not anticipated. German submarine commanders began sharing calculation techniques and attack tactics optimized for electric torpedoes. Günther Prien of U-47, Otto Kretschmer of U-99, and Joachim Schepke of U-100, the aces of the German submarine force, developed variations of Lehmann-Willenbrock's mathematics adapted for different combat scenarios. Prien specialized in attacks against convoys in close formation, using calculations that maximized damage through multiple sequential impacts. Kretschmer developed techniques for nocturnal surface attacks, where electric torpedoes could be fired from extremely close distances without risk of detection. Schepke created tactics for coordinated attacks between multiple U-boats, using G7e torpedoes to create confusion and panic that facilitated subsequent attacks with conventional weapons. Each commander contributed mathematical refinements that were quickly incorporated into the Kriegsmarine's tactical manual. The result was an accelerated evolution of submarine warfare, where the silent mathematics of electric torpedoes became increasingly sophisticated and lethal. The Allies faced not only a new weapon, but a new philosophy of naval combat that challenged all traditional assumptions about anti-submarine warfare. The impact of G7e torpedoes on North Atlantic convoy routes became statistically measurable by late 1942. Reports from the British Admiralty showed a 67% increase in merchant ship losses on routes where electric torpedoes had been confirmedly used. Even more alarming was a 43% reduction in the effectiveness of anti-submarine escorts, measured by the ratio between detected U-boats and U-boats that completed successful attacks. The mathematics was brutal and undeniable. Invisible torpedoes were winning the Battle of the Atlantic. Winston Churchill, in secret memos intercepted by German intelligence, described the situation as an existential crisis for our ability to maintain vital supply lines. The British Prime Minister had understood that the silent revolution was not just a tactical innovation, it was a strategic threat that could determine the outcome of the war. Statistics compiled by the Ministry of War showed that, if current loss rates were maintained, British reserves of fuel, food, and raw materials would be exhausted in 14 months. The mathematics of electric torpedoes was literally calculating the defeat of the British Empire. Each equation solved by commanders like Lehmann-Willenbrock in the depths of the Atlantic translated into tons of lost supplies and British lives at risk. The desperate Allied response to the G7e torpedoes led to the development of increasingly elaborate and costly countermeasures. Project Ultra, already focused on breaking German codes, was expanded to include mathematical analysis of submarine attack patterns. Mathematicians from Cambridge and Oxford collaborated with naval officers to develop algorithms that could predict invisible torpedo attacks based on convoy movements and known U-boat positions. Simultaneously, escort production was massively increased. If individual torpedoes could not be detected, the strategy would be to saturate convoy routes with so many warships that submarine attacks would become statistically improbable. This brute force approach cost the Allies enormous resources. Each additional escort required 200 trained sailors, 1,200 tons of steel, and operational costs of £50,000 per month. The economic mathematics was devastating. The Germans were forcing the Allies to spend 50 times more resources on defense than they invested in attacks. Lehmann-Willenbrock and his colleagues had discovered a form of asymmetric warfare where the silent mathematics of electric torpedoes exponentially multiplied the cost of Allied defense. Each G7e torpedo fired forced the Allies to reallocate massive resources to countermeasures that, at best, were marginally effective. In January 1943, an accidental discovery would dramatically shift the balance of submarine warfare in the Atlantic. During a routine attack against a British convoy, U-96 fired a G7e torpedo that failed to detonate upon hitting the hull of the SS Empire Trader. The torpedo, damaged but still functional, was recovered by Royal Navy divers and transported to technical analysis facilities in Portsmouth. For the first time, Allied engineers could examine in detail the technology that had terrorized their fleets for months. The analysis revealed not only the secrets of electric propulsion, but also the system's inherent vulnerabilities. The lead-acid batteries, though silent, had capacity limitations that severely restricted the torpedo's range and speed. More importantly, engineers discovered that the electric motors created magnetic fields detectable by sufficiently sensitive equipment. This discovery led to the accelerated development of naval magnetic detectors, systems capable of identifying the unique magnetic signature of G7e torpedoes at distances of up to 800 meters. For Lehmann Willenbrock and other German commanders, this revelation represented the end of the era of truly invisible torpedoes. The silent mathematics that had dominated the Atlantic for almost a year was about to meet its technological counterpart. The implementation of Allied magnetic detectors created a new phase in submarine warfare, where the mathematics of electric torpedoes needed to be constantly adapted to overcome evolving countermeasures. Lehmann Willenbrock and other veteran commanders developed sequential multiple firing tactics, where several G7e torpedoes were launched at calculated intervals to overwhelm enemy detection systems. The theory was that, even if the first torpedo was detected, subsequent ones would still have the advantage of surprise during the critical seconds needed for evasive maneuvers. This approach required even more complex calculations, considering not only the trajectory of each individual torpedo, but also the interactions between their magnetic signatures and the response times of Allied defensive systems. Paradoxically, the need to overcome magnetic detectors led to mathematical refinements that made G7e attacks even more precise. German commanders discovered that coordinated firing of multiple torpedoes created magnetic interference patterns that could mask the approach of individual torpedoes. The mathematics of submarine warfare had evolved from simple trajectory calculations to complex analyses of electromagnetic physics applied to naval combat. Even when facing sophisticated countermeasures, electric torpedoes maintained significant advantages over their conventional counterparts. The influence of G7e torpedoes extended far beyond their immediate impact in World War II. The silent mathematics developed by commanders like Lehmann Willenbrock established fundamental principles that would influence the design of submarine weapons for decades. Concepts such as electric propulsion, magnetic guidance, and complex ballistic calculations became standards in modern naval technology. More importantly, the philosophy of invisibility through mathematics, the idea that calculated precision could overcome brute force, transformed into a central principle of contemporary naval warfare. Modern nuclear submarines use torpedo systems that are direct descendants of the German G7e, incorporating advanced electric propulsion, computer guidance, and silent attack capabilities that Lehmann Willenbrock could only dream of. The silent revolution initiated in the dark waters of the North Atlantic continued to evolve through the Cold War and beyond, proving that true military innovation comes not only from superior technology, but from the intelligent mathematical application of fundamental physical principles. Every modern torpedo fired in deep waters carries in its digital DNA the pioneering calculations performed in cramped submarine cabins, where men like Heinrich Lehmann Willenbrock transformed equations into weapons that changed the course of naval history forever.